Hi, my name is Ajua and today we are going to cover the concepts in statistics for anybody that ever struggled with it. So before we get into it, I want to tell you a story. Come closer. A friend of mine who is super sensitive went through her Bachelor of Science degree and Master's wanting to do really well. No, excel. Problem was, she was easily embarrassed and sensitive, and so whenever they were in the lecture the lecturer would explain concepts and she didn't understand, she would just keep it to herself. One day, during her statistics class, the concepts that were covered was just so foreign and so unfamiliar to her that she gathered up the courage to go and see the lecturer after class to ask for clarification. Yet she wasn't game to do it during class. So as she was approaching the lecturer's office, the door was ajar. The lecturer was sitting with his back to the door, and she timidly approached the door and tap, 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 knocked on it. Yes, was the rather abrupt response that came from the lecturer, still seated with his back to the door. And what happened next would cement in her the decision to not ask any questions during her studies. After explaining to the lecturer that she wanted clarification, the lecturer looked at her with a look of disgust and asked, "You want me to do what? You want me to miss out on my lunch and do what again? I just explained everything." Well, if like my friend you have had a joke of a lecturer and have gone through statistics not understanding anything, today you're in luck. We're going to cover the concepts so that you can start to love statistics. Let's do it. Oh, by the way, that friend of mine may or may not have been me. Statistics is concerned with determining whether measured differences between groups or variables are real. What do we mean by real? Real as in whether the differences that we measure or observe based on a sample can be extrapolated to the population at large. Let's look at an example. It will make it so much easier. So suppose you were the 800th passenger of an Airbus A380-800 flight to Wuhan, China at the end of January 2020. When you came back from the trip, you were contacted by health authorities to be tested for COVID-19 because there was mounting evidence that some individuals who had been to Wuhan were presenting with severe acute respiratory infections of unknown cause. So not everyone who had been to Wuhan could be tested, so several people were selected to be tested. So several people were selected to be tested to determine whether there was a higher incidence of the severe acute respiratory infection in people that had traveled to Wuhan. So if we count all the cases of people presenting with a severe respiratory infection who had a history of travel to Wuhan, and then we count the number of people presenting with a severe upper respiratory infection, but no travel history, and we get something like this, where clearly there's so many more people presenting with the disease if they have travel history to Wuhan, then we can say definitely there is a difference. It's not a coincidence. However, if there is a higher incidence, how do we know that the observed differences is not just due to chance? We have to show that it's not due to chance. We can't just say, because we see like 10 times more cases in the people that went to Wuhan versus the people that didn't go to Wuhan, that definitely the differences that we see is real. We have to actually show mathematically, and obviously the branch of statistics allows you to do that. So we determine whether the observed difference is real or not by applying statistical tests. One thing to also be aware of when applying statistical tests is that you can't just collect all the data and then just poke around randomly looking for significant differences. We first have to determine what we are looking for before we do any tests. So we decide on a hypothesis. Yes, that's where the whole hypothesis thing comes in. So in this example, that in the Wuhan example, it would be our hypothesis maybe that we think that people who have visited Wuhan near the end of January 2020 have a higher incidence of the severe acute respiratory infection than those in the general population. So then we get introduced to another key concept in statistics, which is population versus sample. Another concept that we grapple with when we're dealing with statistics is the idea of the level, the probability level that we would accept as significant for any of our measured differences. So usually a 95% probability that there is a difference, and so that would mean a 5% chance that there is no difference. We would accept a 5% chance that there is no difference. This is what's called the null hypothesis. So the null hypothesis, the standard hypothesis is that there is no difference. And then your hypothesis would be that there is a difference, or whatever you're trying to measure, there's a difference between your study case that you're investigating. So in the COVID-19 travel to Wuhan, we would say there is a difference between the people that went to Wuhan versus the people that didn't go to Wuhan. So we would say, yes, there's a difference. That's our test hypothesis. But then in statistics, there's always a default hypothesis, which is that there is no difference. It's all by chance. You're making it all up. Go home. So if we want to prove that it's real, then we have to apply this probability testing. And that's where we set a threshold. We have to show at minimum 95% chance that what we're seeing is not by chance. But before we get into applying a particular statistical test to see whether we have a 95% probability that what we're seeing is real, there are a whole suite of statistical tests that are used depending on the nature of your data. So before we even get into applying statistical tests to see whether we have this 95% probability that what we are seeing is statistically significant or it is real, as we say in normal language, there are a whole heap of summary of the data that we can do, summarization of the collected data. Data can be in the form of categories, for example, sick versus not sick, male versus female, young versus old. That's a categorical data that we've collected. Categorical data is also called nominal data, or it may be referred to as qualitative data, or even non-parametric. Or we could collect data in the form of numbers, numeric data, which, for example, would be the number of days that we spent in Wuhan. A person spent, maybe someone only spent a day, someone spent 3, someone spent 2, someone spent 5, 6, 7, 8, 9, 10, onwards. That's numerical data. Or the weight of a person is a numerical data, or the height of a person. And these are called variables. And what's actually being shown on this screen is the days to onset of symptoms. So maybe in one person, it took 7 days before they showed that they have this respiratory infection, or maybe in the other it was 10. Yet another 12, 13, 14, so on and so forth. So that's a numerical data that we've collected. So it's also called quantitative in some books, or some arenas may refer to it as quantitative data, but it just means that it's a numerical value. After you've collected the data, we're going to summarize it. You're going to use descriptive statistics to summarize the data. So if you collected categorical data, so yes, you know sick, not sick, tall, short, young, old, then you can summarize it by counting up the number of observations in each category. So if we stick to the example of the respiratory infection in people with a history of travel versus those without a history of travel, then we can count the number of cases with a history of travel versus the number of cases without a history of travel, and we can summarize this as a proportion and then multiply by 100 to give the percentages. We can then draw pictures of the data, also known as graphing. I prefer to think of it as pictures. So we then draw graphs with the values that we've got, and for categorical data, you can just use a simple bar chart. What about when we have numeric data? Numeric data is also referred to as quantitative data, or even an interval ratio. So if you have numeric data, you look for the distribution of the data. If when you plot the data, the shape of the data looks a bit like a bell, it is called a bell curve or a normal curve, or the official name for it is a normal distribution. Graphing your data to look at the shape is not just a pretty idea or a nice idea. It's actually required. You should graph your data to look at the distribution, because then you know which statistical test is best to be used for that kind of shape. If the data is normally distributed, okay, we haven't covered it, but we'll be covering normal distribution in a little bit, just in a short bit. But if the data is normally distributed, then you can calculate the average value. The average value is also known as a mean. But after calculating the average, you want to look at how much each individual data point differs from the average. The average that you just calculated, it summarizes the whole data, but then you also want to get a sense of how much each individual point differs from that average, and that's called the standard deviation, how each value deviates from the average, or the mean, as it's also known. So other measures, there are also other measures that of the numeric data that can be used and is sometimes used depending on the distribution or the shape of the data that's been collected. So some of the other measures, people may measure the minimum and the maximum, which is the range. Then they'll look at the median, which is the middle value. And then the interquartile range informs you on the spread around the middle of the data. The box and whisker plot is plotted from your minimum value, your maximum value, interquartile range, so that you can visualize the variability in your data. So for the average, where you calculate an average and the standard deviations, you can look at a histogram. Since you've drawn a histogram, perfect time to talk about the normal distribution, also known as a bell curve, also known as a normal curve. The shape of the normal distribution actually comes from variables found in nature. Variables such as your height, your weight, blood pressure, even exam scores tend to have a normal distribution. And it describes this observation that most of the values will have a tendency to cluster around the center. Fraction will fall significantly outside of the average value. So some of the symbols that you see then, the central value or the mean, also known as the average, will be called, when it's referring to the population, will be called mu, and it's symbolized as mu. It's a Greek letter, mu. And if you are talking about the standard deviation of a population, then we are looking at sigma for the symbol. But don't forget that statistics deals with taking a sample, and then you're trying to see if the sample, any inferences can be made from the sample based on the population. The population is kind of this idea of you will never be able to measure every instance of whatever you're measuring, right? So you take a sample, and that's what statistics is. So statistics then, when we're measuring statistics, we're normally dealing with, instead of the mu, the average, we look at X bar. That's a sample statistic average. And then if we're talking about a standard deviation, where the population uses the symbol sigma for a sample, the statistic is just S for standard deviation. So in the next video, we can look at what to consider when picking the right statistical test, or which, depending on the type of data structure, which tests suit that. But for now, let's do a wrap up of everything we've covered. We've covered quite a lot. We've talked about the idea that you need to have your hypothesis stated up front, because there's this null hypothesis that says whatever differences you're seeing, it is not real. It is by chance. So you need to have your test hypothesis stated up front, and this will inform the kind of data that you are going to collect in order to be able to reject the null hypothesis that there is no difference. We mentioned that to do that, you need at least 95% minimum probability that the difference you're seeing is real. We then talked about summarizing the data that you collected. So if it's categorical data, you count the number of responses in each category, and then you can look at the proportion of that presented as a percentage, and then you can also graph it in a bar chart. If it's numeric data, you can look at the distribution, the spread of the data. If it's normally distributed, you can look at things like the average, and then look at the standard deviation of that. Or you may look at the minimum and maximum range, and you can look at the interquartile range to measure the spread of that numerical data as well. Before you run off, I would love if you can comment on what kind of tests you are doing currently, what kind of statistical tests you've used in the past or are currently using. It's always nice to kind of get a real life story of what's happening. It just makes makes facts much more memorable. So we'll leave it here. Thank you so much for taking time to watch this video. If it was valuable and useful to you, please give it a thumbs up, consider subscribing, and I will see you in the next video. So all the best with your research, whatever you're using statistics in. Bye. God bless.